This is number 30 in the math subset test release questions. Number 30 asks us to solve the uh, following by proving using a mathematical induction the following set. So prove by mathematical induction one over one times two plus one over three times three plus one over four times three times four plus dot 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 plus one over n times n plus one is equal to n over n plus one. So that's what we're trying to show. This is what we're being asked to do. So the process of proving mathematical infinity, so this is the thing. And so our proof, I will use a little bit of shorthand just because writing out and for the sake of space, but your proof should include a little bit more language and also you would want to use full sentences and stuff like that. Okay, so we will go and then I'm going to draw an arrow to this, but I would write that out normally in full detail. We will show a way of mathematical induction. It's really awesome. And you can see, I think that's a T I O N induction. Okay. So our base case here is this is for the set of natural numbers where the natural numbers start with the letter number n. So we're going to let n equal 1 here, and we're going to see that the set is not empty. We're going to make sure that that's the case. Okay, so the left-hand side, if we have 1, plugging in 1 for n here, we get 1 over 1 plus 1. Okay, and that's going to be 1 over 2, where the 2 comes in plus the left-hand side, and the right-hand side. If we plug in 1, we get 1 over 175 plus 1, which is also equal to 1 half. Okay, so when n is equal to 1, this is true. So that shows that the set is not empty. Okay, and so we're going to create our induction hypothesis. Normally you would write out the terms induction hypothesis here. So we're going to assume that 1 over times 2, 1 over 2 times 3 plus that plus 1 over n times n plus 1. We're going to assume that that's equal to n over n plus 1. We're going to assume that that's true. And our induction base step, induction step, okay. What we want to show is that this is true. This is true for the n plus 1 case. Namely, that 1 over 1 times 2 plus 1 over 2 times 3 plus dot 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 1 over n plus 1 n plus 1 plus 1 okay, is equal to n plus 1 over n plus 1 plus 1. Okay, so that's what we're going to try to show. So this is the next case. This is the n plus 1 case. So if it's true, we're assuming it's true for this case. If it's true for the next case, okay, then it's true in general. So we can say that it's true for all natural numbers at that point. Okay, so what we can do is start with the left-hand side, and hopefully we'll arrive at what we're wanting to show. Okay, so our original claim was that a have 1 over 1 times 2 plus 1 over 2 times 3 plus on and on plus 1 over n minus 1 n minus 1 plus 1 1 over n plus 1 plus 1 over n plus 1 n plus 1 plus 1. Okay, so this is what we have. Okay, So we have this. By the induction hypothesis, this right here, by induction hypothesis, we are assuming that that all of these terms are equal to the right-hand side here. We're assuming that this is equal to n over n plus 1, which means that the only thing we have left is this term over here, plus 1 over n plus 1, n plus 1, plus 1. Okay, so we notice that this whole thing collapsed because of our induction hypothesis. And so to simplify this, okay, one thing I noticed is that there's an n plus 1 term, a factor, if you will, a 1 over n plus 1 term specifically, that I can factor out. So I'm going to do that and then see about maybe combining uh, the, the two resultant fractions to see if there's maybe something algebraically we can do to make it kind of move over to what we're trying to show. Okay. So this term and this term in the denominator are common factors. So I'm going to pull those out. 1 over n plus 1. Okay, so what do I have left over? Well, this is gone, so it's just n over something plus, and this is gone, so I have 1 over, what's this, n plus 1 plus 1? Well, I'm going to simplify that because n plus 1 becomes n plus 2. Okay, which means that this has a 1 on it in the denominator, and I need it to be an n plus 2. So I'm going to multiply top and bottom here, make n plus 2. Try and squeeze it in right here, n plus 2. Okay. So n plus 2 times that, and n times 2 times that. That'll give me a common denominator, and then it'll allow me to combine like terms. So if I do that, I'll do that over here. I have 1 over n plus 1 on the outside. I'm kind of sneaking back to where I'm trying to show. I don't see an n plus 1, so I'm trying to remember that's where our target is. So let's see what else we can pull together. So I have an n plus 1 times n, so I'm going to distribute that through, so that's n squared plus 2n plus 1. The n squared coming from here, and then n times 2 gives me the 2n plus 1. The plus 1's from here. And then I have an n plus 2 in the denominator. Okay. As I'm looking through this looks like it's a little bit far away from this. But I noticed that this is a trinomial, and so it looks like it might be verbal. And if you notice that this is in fact 1 times 1 is the only factors of this, and it's adding that would add to 2. This actually factors as a perfect square trinomial, so this is equal to n plus 1 times n plus 1. There are 2 n plus 1 terms here. And then I have in the, so I'm factoring this, I can bring this n plus 1 back inside. So I have n plus 1 times n plus 2. Just removing dropping the parentheses and factoring this. Okay, and then notice I have a common factor of n plus 1 in the numerator and denominator. So those can be reduced. And so I'm left with n plus 1 over n plus 1 over n plus 2. Now this is looking much closer to what we were trying to prove. But I have a n plus 2, and I need an n plus 1. It's 1. So I look, and I go, oh, but 1 plus 1 is equal to 2. So I can actually write this into one more step as n plus 1 plus 1. And if I see it as kind of like this is the term that I'm looking for, then this shows that this is indeed exactly what we want to show. Therefore, thus, by the principle of mathematical induction, you would write that out. Thus, by the principle of mathematical induction, we have what we wanted to do. 1 over 1.2 plus 1 over 2 times 3 plus dot 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 plus 1 over n times n plus 1 is equal to n over n plus 1. And that is what we were hoping to share. I hope this video was helpful, and I look forward to seeing you in the next one.